In the implementation of field-oriented control, or FOC, the generation of these sinusoidal signals is the primary task that must be performed. There are several methods for generating sinusoidal voltage signals using PWM techniques. Two of the most common being SVPWM, or sinusoidal PWM, and SVPWM, or space vector PWM. Both utilize PWM modulation to control the average voltage magnitude across each motor phase. However, in DC systems, we cannot directly generate negative voltages. Therefore, the sinusoidal signal we create must be shifted upward so that all its values are above 0 volt, allowing it to be modulated using PWM. However, it is important to note that in a three-phase motor, what matters is not the voltage relative to ground or 0 volt, but the voltage difference between phases. If we calculate, the maximum difference between the highest and lowest phases in a sinusoidal waveform only reaches approximately 0.866 times VDC, meaning we are not fully utilizing the supply voltage. This is a drawback, as the current that can be delivered to the motor is limited by the amplitude of this signal. To overcome this limitation, we increase the voltage difference between phases until it reaches the full VDC. Thus, the sinusoidal signal will increase to 1.1547 times. From here, we can see that the portion above VDC and below 0 is impossible to apply with PWM. Therefore, we must shift the signal up and down, like a triangle shape derived from the average between the highest phase and the lowest phase, so that the highest phase and the lowest phase do not exceed the VDC and ground limits. This results in the following space vector waveform shape, and that is why the space vector is more advantageous than the sinusoidal waveform. With the same VDC, we can achieve greater torque with SVPWM.